Hello everybody and welcome back to another video with me, Miss Martins. Today we're doing a really awesome topic, a very important topic. So this video is really important and relevant for grade 10, 11 and 12 students, and it's called the Quantitative Aspects of Chemical Change, or Stoichiometry. Let's jump right in. Stoichiometry, I like to call it the maths of chemistry, and this is where a lot of students freak out because they see maths involved, numbers, formulas, and they freak out, they make silly mistakes, they don't know where to start, but I've got you. So I've gotten a few steps, I've written out a few steps for you, and I've said these are kind of things that you need to follow when answering a stoichiometric question. So my first point that I made is that formulas are important. We're always going to use them as they're given on the formula sheet. So when you write your exam, you will see your formulas given like this, as well as your physical constants. When you select a formula to be used, you always need to write it down as it's written on the formula sheet. If you want to rearrange the variables or manipulate them, you can do that after the fact. So you always have to write down the formula on the formula sheet, then manipulate it, and please make sure that you rearrange or manipulate equations correctly. We'll go through that when we break down the formulas. Then I said you need to understand the symbols or the quantities. So basically, what does N mean? What does M mean? And so on. Substitution, that's when we put the numbers into the variables. Solving correctly. Now, the reason I put correctly in caps is because sometimes people do basic maths wrong. So they get the physics right, they choose the correct formula, they sub the numbers incorrectly, but then they solve incorrectly. And you always need to put the correct unit at the end. If you don't put the unit, you don't get the mark. In terms of the formula sheet, there will be a few variables that we will use in the stoichiometry section. So we'll use molar gas volume at STP, and we will make reference to standard temperature, standard pressure, things like that. But these are the formulas that I want us to look more closely at and kind of break down what they mean and what the variables mean. We will be going through these one by one, but just as a matter of being brief and going over them. This formula allows us to calculate number of moles, which is N. That's mass and molar mass. This is the formula we use for concentration of solutions. This is the formula we use to work out number of particles or number of atoms or number of molecules. And this is the formula we use to work out the volume of a gas, either at STP or at other temperatures and pressures. The question will mention it to you. Another thing that is very important when it comes to stoichiometry is using your periodic table. Again, this will be given to you in the exam, but you need to know how to use it properly. So when working out the molar mass of a compound, for example, we use the atomic mass numbers, the relative atomic mass numbers, which is the big number. So if I ask you to work out the molar mass of a compound like NaCl, you'll say, okay, sodium is Na. It has a molar mass of 23. So you'll go 23. Chlorine has a molar mass of 35,5. So 23 plus 35,5. And that gets us 58,5 grams per mole. So knowing how to use your periodic table, what the elements are, you absolutely need to know that. So if you struggle with understanding what the elements are and struggling with naming and balancing, you need to check out some of my other videos. Right. Then it's super important to understand your quantities, your physical quantities, your variables, and their units. So just using this formula as an example, concentration is represented by C. So C is concentration. The symbol to represent concentration is C. So if I want to say the concentration of a solution, I say C equals. Then if I want to give the unit is moles per cubic decimeter. Now, you need to understand the difference between a unit, which is always how we end off a question. An answer always ends with a unit, and the symbol, which in this case is C. So for volume, for example, the symbol is V, but the unit in stoichiometry is cubic decimeters. You need to know those things. So this is a little bit of a summary table to help you know the difference between the quantity and the symbol and the unit that it is measured in. They may give you a question where they say a certain solution of 3 moles per cubic decimeter, and then at a volume of whatever, and you need to know moles per cubic decimeter. that means concentration. They might not mention the word concentration, but by you looking at the unit, you can figure out, okay, cool, that 3 is concentration. I hope that's making sense. Then the very next thing that I want to speak about before we go through the formulas is you need to know how to write your formulas correctly and solve properly. So for example, if I say work out the volume of a 3 mole solution with a concentration of 6 moles per cubic decimeter. Now, first of all, they're being nice because they're telling you that this is concentration. So concentration is 6 moles per cubic decimeter. Then we also have moles that's given over here. So that's N, 3 moles. And then they want us to work out the volume. So if you look at the formulas that have been, the variables that have been given, we know by looking at our formula sheets that we're going to select this formula, the one that I spoke about earlier, in order to answer this question. So you need to write down the formula properly as is on the formula sheet. Then you may rearrange it, but I generally just go and sub in from here. So concentration is 6, N, number of moles, is 3, and V is volume. Now you need to know, and I know this might sound silly to some of you, but you need to know how to solve for volume correctly. It's not 6 times 3. What happens when the variable is in the denominator like it is over here is the variable, because it's in the denominator, swaps places with this thing here on the left. So what I mean is the volume goes in the place of the 6, and then it goes 3 divided by 6. 3 divided by 6 is a half, so my volume is 0,5, and you can't just write 0,5. You need to give me a unit, and like I mentioned, the standard, the SI unit for volume, the one that we use if we use this formula, is cubic decimeters. I will explain why it's cubic decimeters and how that makes sense when we go through the formulas, but it makes a little bit of sense if you look at the unit for concentration, which is mole per cubic decimeter, and this is mole. So if that's mole per cubic decimeter and that's mole, the unit for volume, it makes sense that it's cubic decimeter. Now I've broken down each formula and I'm basically put a little summary of when do I use this formula, and we're going to explain what these symbols mean. So N is number of mole, okay, number of moles. Now, I will do a separate video on moles and what the heck a mole is, but basically, a mole is the SI unit used to measure the amount of any given substance. You need to understand that chemical reactions take place at a level that is very, very, very tiny, 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 tiny particles and hundreds of thousands of particles. So measuring reactions in terms of grams wouldn't make sense. A mole is basically a quantity of anything that has the same number of particles found in 12 grams of carbon-12. That is one way to define it. It's basically, the number of particles is basically 6,02 times 10 to the 23 particles, which is Avogadro's number, which we'll get to in a second. So a mole is basically a unit of measurement, just like mass is a unit of measurement. So if I have to say to you a mole of carbon atoms, that will be 6,02 times 10 to the 23 carbon atoms. If I have to say to you I have a mole of chocolates, that'll be 6,02 times 10 to the 23 chocolates. It's kind of like when someone says, oh, I'm going to bake a cake and I need a dozen eggs. A dozen eggs means 12 eggs. So 1 mole means 6,02 times 10 to the 23 particles. I hope that sort of makes sense. Then baby m is mass in grams. If they give it to you in kilograms, you absolutely have to convert. I remember that it's in grams because grams are smaller than kilograms, and chemistry deals with small things. Big M is molar mass, and it's measured in grams per mole. The reason it's measured in grams per mole is because moles is measured in mole, and mass is measured in grams. So if I swap M and N, I'm going to get the following. Molar mass is equal to, that's big M, is equal to baby m over little n. So it's grams per mole. I hope that makes sense. It's nice to know why the units are the way they are, so you can figure it out by looking at the formula. And we get molar mass big M from the periodic table like I showed you a few minutes ago. So we use this formula, baby N is equal to little m over big M, when they ask you to find the number of moles, which is N, or if they ask you to find the mass and you're given the number of moles. So if we're trying to find baby M or N, we use this one. Here's an example. How many moles, so we're looking for moles, which is N, are there in 20 grams, that's baby M, of calcium carbonate? We're trying to find N, we have little m. Big M comes from the periodic table. If you go look at calcium plus carbon plus 3 of oxygen, you will figure out that big M is 100 grams per mole. Go check it out for yourself. So therefore, how we answer this question is we write our formula first. You substitute in what you're given. So we're given mass, so that's 20. We're given molar mass, which is 100. Well, we weren't given 100. We figured it out from the periodic table, but we could figure it out from the periodic table because we were given the compound. Okay, so calcium is 40, carbon is 12, and oxygen is 16, but I need to multiply it by 3 because I have 3 oxygens in my compound. And that leaves us with 0.2 mole. That's your answer. Formula, substitution, answer. Our next formula also involves N, baby N, which is number of moles, but here we see we have a big N as well, and Na. Now Na is called Avogadro's constant, which we spoke about, Avogadro's number, and that will always be found on the data sheet. Now some data sheets round off to 6.02 times 10 to the 23, and big N is number of particles, compounds, formula units. So we use this formula when they ask us to find number of moles and they give us number of atoms, molecules, or particles, or if they ask for the number of particles, compounds, atoms. Now, this is a little bit of a longer example. So they say how many oxygen atoms are there in 10 grams of MgSO4 magnesium sulfate. Now you can't say, look at magnesium sulfate and say, oh, there's 4 oxygen atoms. Yes, that is true. There are 4 oxygen atoms in one molecule, but we don't know how many molecules or how many of these particles we have in 10 grams. So what we have to do first is we have to find out the number of magnesium sulfate compounds, how many particles, and then once we have that number, we can times that by 4, because in one of these molecules there's 4 oxygen atoms. So if I have 2 of them, then I'll have 8 oxygen atoms. If I have 3 of these things, I'll have 12 oxygen atoms. I hope you know what I'm saying. So we're first going to find N, which will be number of magnesium sulfate compounds. But if you look at what we're given, I hope you can see, or I hope you notice the issue. We're looking for N. This one is our constant, which is 6.02 times 10 to the 23. We don't know number of moles. We do know mass in grams. So what we're going to have to do first is we're first going to have to find number of moles using this formula. And then once we have number of moles, then we can substitute that in this formula, sub in the constant, and get the number of magnesium sulfate particles. So our first step is we're going to substitute in the mass, which is 10 grams. Then we're going to substitute in the molar mass. We just have to work that out quickly. The molar mass of magnesium sulfate, we look at the periodic table, we look at the atomic mass number of magnesium, plus the atomic mass number of sulfur, plus 4 times the atomic mass number of oxygen. So magnesium is 24, sulfur is 12. There's 4 oxygens and oxygen is 16. So we get 100 grams per mole, and that goes in the place of big M. So our number of moles of magnesium sulfate in 10 grams is 0.1 mole. Now that we have N, number of moles, we can use this formula to get number of magnesium sulfate particles. So we write that formula now. Now I'm going to sub in 0.1 in the place of N. Now please just take note, if this was a weird, long, recurring decimal or a non-terminating decimal, so in other words a decimal number that goes on and on and on and on and on and doesn't stop, you can't round that off. So you either put in the entire decimal number here or you put the fraction in here, but you can't round off in the middle of a question. Then big N is what we're looking for, and NA, that is Avogadro's number or Avogadro's constant. So what we're going to do is we're going to take that over. It's going to be 0,1 multiplied by Avogadro's number. And we get 6,02 times 10 to the 22 magnesium sulfate molecules or compounds. Now that looks almost like Avogadro's number. It's because we took Avogadro's number and multiplied it by 0,1. But the important thing to notice here is the sum is still not done. We wanted the number of oxygen atoms. But what we've gotten so far is we've gotten the number of magnesium sulfate molecules. Now remember at the beginning of the question, I said that in each of these, each magnesium sulfate has 4 oxygen atoms. So if I have 2 magnesium sulfates, I'm going to have 8. If I have 10 magnesium sulfates, I'm going to have 40. So basically we multiply the number of magnesium sulfates with our number of oxygen atoms. So therefore, the number of oxygen atoms in magnesium sulfate is that number, 6,02 times 10 to the 22 multiplied by 4. Why 4? Because there's 4 oxygen atoms in each of these. And there's your final answer, 2,408 times 10 to the 23 oxygen atoms. Our next formula is C is equal to N over V, or this is a combined formula, C is equal to baby M divided by big M multiplied by V. Now the reason why there's 2 formulas over here is because to get the second formula that you see over here that I'm circling, they combined the first one with my N is equal to baby M over big M. So combining these two, if I add those 2 formulas together, if I substitute M over M, moles over molar mass, into the place of N, you're going to end up with this formula. So when do I use this formula? Well, let's first actually see what the different things mean. So N is number of moles, as we've mentioned before. C is concentration, measured in moles per cubic decimeter. And V is volume, measured in cubic decimeters. Now, it's very important to remember that when you use this formula, your volume has to be in cubic decimeters. Has to. And often they'll give it to you in cubic centimeters. So to get that to cubic decimeters, we're going to divide by 1,000. That's a very important thing to take note of. Now, I just want to explain why the unit for concentration is moles per cubic decimeter. Moles, the unit for moles is mole. The unit for volume is cubic decimeter. So we're basically saying moles divided by cubic decimeters. If I take this up to the top, we know that when we bring something to the top of a fraction, the exponent over there will become a negative exponent. So that's where the unit comes from. So it's once again, it's very nice to understand that. So we use this formula when you are asked to find the concentration of a solution, if you're given the mass or the moles and the volume. Or we can work backwards and find the volume if you're given moles or mass. In this example, we're given 200 grams of sodium chloride, and they say it's dissolved in 2 cubic decimeters of water. So when we're taking a solute and dissolving it in the solvent, which is water, we're going to form a solution, and they want the concentration of the solution. So we want C, but we need to look at the other bits of information. So this over here is mass, and it's in grams, so I'm happy with that. We don't have to convert. And they give us the volume in cubic decimeters, which again, that is the good unit. It must be in cubic decimeters. Determine the concentration. So if you look at what we have, you can look at our first formula and you can see, it doesn't really make sense to use this one at the moment, because although I have volume, I don't have number of moles. So what we can do is we can either work out number of moles first by using this formula. We'll have to sub in our mass, and we'll have to work out our molar mass by looking at the molar mass of sodium chloride. Sodium chloride is NaCl. So we can definitely do that. Or we can use this combined formula over here, which is what I'm going to do. So I'm going to take the combined formula. Remember, the combined formula just basically incorporates both of these formulas into one. So I'm going to sub in my mass, which is 200. Divide that by my molar mass. Now we have to first work out molar mass. The molar mass is the atomic mass of sodium, which is 23. You can look on your periodic table, plus the the atomic mass of chlorine, which is 34. 5,5. Again, look at your periodic table. That is 58,5 grams per mole. So that's what I'm going to substitute in there to molar mass, 58.5, and my volume is 2. Now remember, MV, that means multiply. M times V. Type that into your calculator, and we get 1,71. I rounded it off to 2 decimal places. My calculator says 1,7094 blah blah blah, but in physical sciences and chemistry the rule is you have to round off to at least 2 decimals. So if I want to leave more decimals, I may do that, but I just chose to chop the number off there to round off there. So 1,71 moles per cubic decimeter. My last formula over here is N is equal to V over Vm, and I wrote here that it's very important to only use this formula for gases, only gases, and volume must be in cubic decimeters. So like I mentioned earlier, to convert from cubic centimeters to cubic decimeters, we have to divide by 1,000. N is number of moles, V is volume as we mentioned. Now Vm is molar volume, that's what it means. And this is a constant, which means it stays the same if your temperature and pressure is at standard temperature and pressure. So the question will say the reaction takes place at STP. If the question says that, then this value over here is 22,4. If the question says the reaction does not take place at STP, they must provide you with the molar volume. So maybe it'll be 23 or 25 or whatever they tell you. So we use this formula when I want to work out the volume of a gas, so a reactant or a product, and or number of moles if the volume of a gas at STP is given. In my example, I ask you to work out the number of moles of a 200 cubic centimeter gas at STP. So we know we are looking for number of moles, that's N, question mark. The volume that they give me is 200 cubic centimeters. So like I said, that 200 cubic centimeters, we need to convert that to cubic decimeters. We need to divide it by 1,000. So that is 0,2 cubic decimeters. And because they say at STP, we know that the molar volume is 22,4. We take our formula, write the formula first, substitute in, and get an answer. So we get 0,0089 mole. Remember, this is not to 2 decimal places, but the rule is it must be to at least 2 decimal places. So if it's a small number, I generally include a few more decimal places, but if you want to make it to 2 decimal places, you will basically chop the number off after 2 decimal places, which is over here. Because this number is 5 or more, it causes that number over there to get 1 bigger, so 0,01 mole. I hope you enjoyed this video, and please remember to check out my other videos on stoichiometry and my other videos on chemistry. We tackle exam level questions. So I hope to see you in the next video. If you haven't subscribed yet, make sure to hit the subscribe button and give this video a thumbs up. See you soon, everyone.